Jai Hind to all. My name is Dr. Divya Sharma, Assistant Professor in Anjay Kumar Engineering College, Ghaziabad. Now, today's video lecture is on VLSI. It's VLSI Design. Its code is PEC 701. Now, today's topic is testing. So, first we will start with the introduction of testing. Now, as you all know that there is a in VLSI flow, there is a complexity which is increasing. So that's why there is a functional testing, exhaustive functional testing becomes impractical due to this exponential increase in possible input combinations. So therefore, design for testability techniques are incorporated for this design phase to make post fabrication testing efficient and reliable. Now there are some strategies for testing, design for testing. First one is scan design. Second is built-in self-test, that is also BIST. Now third is boundary scan, that is also known as IEEE 1149.1 JTAG. Now the next is test point insertion. So we will discuss all these strategies or all these techniques of this design for testing. We will discuss one by one. Now first one is scan design. So when we are inserting scan chain like a shift register, then that is used to control and observe internal flip-flops of the circuit. Now second is built-in self-test. So that enables the chip to test itself for the circuit and using internal generated test pattern and response analyzers. Now third is boundary scan. So it provides a standard interfacing for board level testing and debugging in the circuit. Now the next is test point insertion. So it improves fault observability and controllability. Now these strategies, these techniques reduce test time, improve fault coverage and minimize test cost that ensures defective chips are detected early in the manufacturing time of the chip. Now this is a simulation for design verification. First, we have to specify all the input variables in this specification steps. Let it be, we have to design an AND gate. So if we have to design an AND gate, so what are the inputs and what are the outputs we have to consider for that two input AND gate? So let it be C is equal to A into B. AND means multiplication. So these are the inputs A and B we have to consider, and C is the output. We have to consider C is the output. So how many inputs are required for the designing of an AND gate? So two inputs A and B, and C is the output. So these variables we have to design in the specification. Now next is synthesis. Now if we have to synthesize this AND gate, so we have to take our design net list. We have to synthesize here. What we have to do, we have to define a dot product in between A and B. So we have to create a net list for designing of an AND gate. Now here true value simulator. So this block is used to we have to apply a logic implementation on this AND gate, and here inputs from this specification, inputs are stimuli from in this step from this specification. So here we have to compute this response, means we have to compute this AND gate. We are getting the output at this point where computed responses. So here we are getting the output C for these inputs A and B. Now response analyzer. So here this is the output for this AND gate, means we are getting output for this C is at this step computed response. But here is a response analyzer, means we have to compare here the responses of the actual response and the computed response. Here we have to analyze these two, means we have to take a comparison in between these two. If there is an error, then we have to design again, we have to do changes in the design. Here we have to design a netlist, so we have to do changes here in this block. and if we are getting an error. If there is no error, then you will get the correct output. So this is the simulation for design verification. Now here, what are the steps we have to follow when we have to verify the circuit design, or we have to verify the netlist for any circuit, or for any logic implementation. So we have to meet the functional specification before manufacturing the chip, or before the fabrication of the chip. So first is specification. Now in this step, this defines what the circuit should do, means what we have to do. We have to implement an AND gate or anything. What implementation we have to do. Here it defines what circuit should do. It means we have to design a logic function here. It means performance, means what should be the output, means we have to decide here the goals for that circuit. Now timings, etc. So it is a starting point of the design process, where we have to design, where we have to define what should be the circuit should do, and what implementation we have to do. We have to decide at this point. Now second is synthesize. Now synthesis is where specification is done, and that is translated into an actual circuit design. So usually in terms of netlist, means netlist means how many gates we have to take, what are the connection we have to do. So these all are in this synthesis process. So the result is in the form of design netlist block. So here next is design netlist. So this represents the hardware structure that will implement the given specification, and that needs to verify here before fabrication, and we have to check it behaves correctly or not. Now next step is input stimuli. So these are the test vectors, or we can say these are the input signals applied to the design during the simulation. So we have to apply the input from this input stimuli to the design process. Now here this mimic the role is the real inputs that the circuit will receive in the operation. Now next step is the true value simulator. So here where we have to use a simulator tool that simulates the logic behavior, means we have to take an example of AND gate. So we have to here simulate the logic behavior of the circuit and from using the netlist. Now it computes the circuit will respond to the input stimuli and produces here computed response from that logic. Now here computed response, these are the simulated outputs obtained from the true value simulator. जो भी आपको output यहाँ से मिला है, that is simulated here. Now here response analysis. So the computed response which we are getting from the circuit and what should be the actual response. So we have to compare the computed response and the actual response. If there is an error, then we have to repeat the whole process. If there is no error, then we can do the fabrication. So here computed response are compared with the expected correct results, or you can say the actual results. So we have to take a difference in here, and if there is a difference, we are finding here any difference, then that is known as design error. If there is no error, then we have to do the final step. If there is an error, then we have to design the changes. It means if there is a mismatch in the output response, then designer have to modify or debug the design and re-simulate it again and until the computed and expected responses matches. So we have to do this process whenever we are not getting the actual response, actual expected response. Now in the last step, we have to do a verification loop. So here in the verification loop, the entire process forms a loop. It means first we have to do the specification, then we have to go to the second step, design. Then design means here we are doing specification, we are giving here inputs A, B, C, D, jo bhi hai. Now here we have to design a process. Let it be if we have to design an AND gate, so we have to provide here a logic in between A and B, and that comes in the output C. So here we have to do a simulation by a software tool. Then here we are getting the output and we have to compare the output, computed response and the actual response, and we have to do a comparison here. And if your design is corrected, then we have to do the, then we are getting this actual output. If we are getting the actual output, means if there is no error, then we have to do a fabrication process. So that is, it means here we have to check design is correct or not. If design is not correct, then we have to go to the design process again. So this continues until the design behaves as a specified. Now next topic is defects. So when we are doing a fabrication, there are so many defects are there. So what do you mean by, first what we have to understand, what do you mean by defect? Now defect means there is a physical cause at the device, or you can say in a material level. So that is known as defect. A defect is physical, or you can say a physical imperfection or unintended variation in the manufacturing hardware compared to the intended design. So it can originate from during the fabrication, during the material process, or we can say due to aging, means due to so many years are there for the device, then you can say then there may be a defect. Let us take an example. These are the types of defects are there. Process defect, material defect means defect, it may be in process, it may be in material, it may be in aging defect, it may be in packaging defect. So what do you mean by process defect? So here it may be missing contact windows are there, or maybe oxide breakdown, or maybe unwanted parasitic transistors are there. So you can say if this happens in the device, then you can say there is a process defect. Now second is material defect. If there is a crystal imperfection, cracks are there, surface contamination are there, so you can say that if these types of defects are there, then you can say these are material defects. Now the next is age defects. Now if dielectric breakdown is there, electromigration is there, so these defects are present in the device, then you can say that is due to age defects. Now fourth one is package defects. So contact degradation or seal leaks are there. So these are the defects are there in the material, then you can say there is a packaging defect. Now what do you mean by error? This means these are the defects are there. Error means error is an effect, or you can say error is an effect of a defect. Now error is a wrong output signal, or you can say behavior that appears because of defect in the system. It can be observable effect of a defect. Now let us take an example. If we have a broken connection, or you can say defect causes a logic gate output to stay stuck at 0, but when it should be 1, means it should be 1 but it is stuck at 0, that means wrong output, we are getting the wrong output, it means there is an error. Now fault. Now first is defect, you should know what are the types of defects are there. Now second is that error means effect of a defect. Now third term is fault. What do you mean by fault? So fault is a model abstraction form of a physical defect. Fault, it is a logical or functional representation of a defect at a circuit, or you can say a system level. In testing, we model physical defects such as faults to detect them, usually using simulation or testing vectors. Let us take an example. That stuck at fault means line permanently at 0 or 1. Means stuck at fault means it may be stuck at 0 or it may be stuck at 0. Output should be 1 but we are getting here 0. Output should be 0 but stuck at 1 means output, we are getting the output 1. Now bridging fault. So bridging fault is in between two lines sorted. If two lines sorted are there in the circuit, then you can say that is known as a bridging fault. Now open fault, it means broken connection is broken here in the circuit, then you can say that is a type of open fault. So these are the faults are there: stuck at fault, bridging fault and open fault. Now if we are comparing these three terms, what we have studied, first is defect, second is fault, third one is error. Means first one is defect, then error, then we have done with the fault. So if we are comparing these three on the level, then we can say defect means defect is at the physical level. For error is, it means behavior of the behavior of a circuit. Then fault is, it may be in the logical or functional. Now, what is the meaning of defect? Defect already we have done. Defect is actual manufacturing or material imperfection. Fault means abstract representation of defect using for testing. Now, error, if we are getting error, means wrong output in place of the actual. If your output should be 1 then, and you are getting the 0, then it means there is an error. So, wrong output observed due to fault or defect. Now, here, if we have to take an example of defect, then we can take an example of defect is that broken contact or oxide broken, then you can say there is a defect in the device. Now, fault, it's stuck at 0 or short or open, then you can say these are the types of faults are there in the device. Now, error, already we have done that if you are getting the incorrect output signal, that is known as error in the device. Now, fault types and models. So, first is physical defect. Already we have done that these are the faults that occur due to fabrication or design due to imperfections in the materials and process. We can take an example that defects in the silicon substrate, photolithographic defects, mass contamination and scratches are there. Now, process variation abnormalities and oxide defect. So, these are types of physical defect. Now, in a device, there may be physical defect, there may be electrical defect. So, what are the electrical faults are there? So, physical defects that often lead to electrical faults that affect the circuit operation or circuit performance. Now, what are the examples? We can say that these are electrical faults. First, there may be bridge faults, there may be open faults, transistor stuck on or stuck open. Now, resistive shorts and open, excessive change in the threshold voltage, excessive steady state current. So, these are the types of electrical faults are there in the device. Now, the third is logical fault. So, logical means we are talking about 0 or 1. So, electrical fault can be represented at higher level as a logical fault. Now, here we are taking an example, logical stuck at 0 or 1, or it may be a slow transition, means delay in the fault. Now, AND bridging or OR bridging. So, these are the types of faults are there. So, we can see the structure that here is a defect. When you are seeing this is a contact and here this is a layout. So, this is a defect here. Now, you can see here this is a resistive short defect. Now, here your output should be here 1. If this is 0, this is 1. So, this is OR gate. So, your output is here. It should be 0 or let it be here. This is 1. So, 1 plus 1 is 1, but it is stuck at 0. So, you are getting here 0. So, there is an error in the output of this logic gate. Now, these are the types of faults are there: stuck at 1, stuck on, stuck off and bridging. Now, first we will discuss stuck at 1. So, this means node permanently fixed to 1. It means node is connected to VDD, permanently connected to VDD, means there is a fixation of this one, and here you can say logical error effect is there. Now, second is stuck on. Now, transistor always on, it means leakage contention is there. Now, stuck off, it means transistor always off, it means delay or logic failure is there. Now, the fourth one is bridging. Bridging is that there is a short in between two lines, that is known as wrong logic level or short circuit is there. So, these are the types of faults are there in the device. Now, stuck at fault. So, you can see here is a MOS transistor is stuck open. Here it is open here. So, stuck open fault is there, and now here short is there. So, it is known as stuck on fault is there. Now, stuck at fault. So, single stuck at fault is independent of the technology or design style. So, test for single stuck at faults or cover a large percentage of multiple stuck at faults or unmodeled physical defects. Now, what do you mean by delay fault? So if there is a delay, means let it be timing failure, the target operating speed can be caused by several factors. First, it may be incorrect estimation of on-chip interconnect delay or timing parameters. Second is process variation, that changes in the circuit delay, or you can say clock skews. Now third one is open in metal lines that connecting two parallel transistors are there, that reduces the affected transistor width. Now the fourth one is aging effect, such as hot carrier induced delay increases is there in the device. Now next topic is controllability and observability. So first, what do you mean by controllability and observability? If there is a circuit, then we can observe the output, we can observe the inputs, how we can control the circuit, that there should be a correct output at the circuit, at the implemented circuit. So what do you mean by controllability? How we can control the output, it should be correct or not. So it is a measure how easily a test engineer can set a desired logical value 0 and 1 at a particular node in the circuit. Or you can say it is achieved by applying suitable values at the primary input variable, input terminal. Now second is observability. It measures how easily a signal value at internal node can be observed at a circuit primary output, and it can be determined by controlling inputs and monitoring outputs. So if we have to note down here, the term primary refers to input-output boundaries of the circuit under test, and degree of the controllability and observability determines the testability of the circuit. Now, testability can be evaluated based on whether test vectors are generated deterministically or randomly. Now, let us take an example. We can take an example where we have an AND gate, in 3-input AND gate. Here OR gate is there, 3-input OR gate, NOT gate, and here is NOR gate is there. So in this circuit, these 4 gates are there, and how many inputs? A, B, C are your inputs, and output for this AND gate is at point 10, and output for this OR gate is at point 7, and output for this NOT gate is at point 11, and output for this NOR gate is at point 12, and finally we are getting output with this F. So here we can see output of this AND gate depends on input A and B, and this input and this output which is generated from this OR gate. And here this OR gate output depends on the input B, C and D, right? So here if we have to do a testability, so we have to detect test line this 8. This can be tested by, we can get this test line, we can get this input of this AND gate from this output of this OR gate, and it depends on all these outputs. So we can test this circuit when you should know these inputs A, B, C, D. If we know this if we know this input B, C, D, then we can find out this 7 output for this OR gate, and if know this, then you can get this output 11. Now, if we know this input, then this is known input for this AND gate. If we are applying this A and B inputs for this AND gate, then we will get the output of this 10, means output of this AND gate. If you know this AND output of this AND gate and output of this NOT gate, then we are getting this final output. So these are the steps we have to follow to get this output F. So we can do a testing on this circuit only when we are applying correct input variables A, B, C, D, then only we get the output, correct output at the final destination. Now, next is ad hoc testing design technique. Now, what is the purpose of this ad hoc DFT, means design for testing technique? So, there is a main goal of this ad hoc DFT, design for testability technique, is to improve the testability of stuck at faults. So, these methods are based on good design practices that have been learned from the experience of this process. Now, first here is partition and mux technique. So, when a circuit contains many serial gates, functional blocks, large modules, so it is very difficult to test all these in a single circuit. So we have to make a testing easier. The circuit divides into smaller partition. So we can take an example. Let it be, we are taking this example. This is the whole circuit and we are doing a partitioning here. This is partition 1, then 2, then 3, then 4, then you are getting the output. So we have to test here first sub-circuit 1, then we have to test this sub-circuit 2. Means first when we are doing testing for this sub-circuit 1, then we are getting output, and output totally depend on this input. If we are applying correct input, then we are getting the correct output, and that correct output works as an incorrect input for this sub-circuit 2. If here input means what should be the output of this sub-circuit 1, if it is correct, then you are getting the correct output for this sub-circuit 2. Now here multiplexer is connected and that is controlled by this control input 1, and here is also multiplexer that is controlled by this control input 2. Now here, if here this is correct input, control input is given to this multiplexer, then we are getting output for this, correct output for this multiplexer, and if this is correct, then we are getting the output correct for this sub-circuit, and finally we are getting the correct output for this circuit, which this is a whole complex circuit and we are dividing this circuit into sub parts. Then we are doing a testing, and if your input variables for all these in this all sub parts all are correct, then we are getting the final correct output for this whole circuit. Now what are the advantages of this ad hoc testing design testability? So it increases accessibility of the internal nodes. Now second is reduces number of test patterns required. So it speed up overall testing process. Now let us take an example of 32-bit counters. So we can divide into 16-bit parts, means two 16-bit parts. Then we can apply here testing and easily we can do a testing for this 32-bit counter. Now what are the disadvantages for this ad hoc testing design technique? So adding multiplexer and partitioning the circuit that can lead to increased chip area and slightly higher circuit delay. So these are the disadvantages of this ad hoc testing design technique. Now next technique is scan path design. So it is used for DFT, mostly used for DFT, means design for testability. Now scan path can be inserted into a known scan sequential circuit netlist in an automated way. What is actually done? All the flip-flops are required or replaced by scan flip-flops, and connect the scan flip-flops as configurable shift register. Now add one test control primary input for the circuit and add a scan in input and scan out output for the shift register in a circuit. Let us take an example. This is a scan flip. This is a master slave D flip-flop. So we have to do here scan based technique. So this is a master latch and this one is a slave latch. Now whole this master slave flip-flop depends on this. Now here there is a data input. This is a test control and here is a scan data input. So here this master slave flip-flop depend on data input and test control and scan data input. So here if test control is 1, it operates in normal mode, means multiplexer selects D input. If test control is 0, it operates in test scan mode. So multiplexer selects SD, means scan data input. So this allow internal registers to be connected in a scan chain for testing and debugging process. So this is the process of scan based testing procedure. Now here we can refer this book Kang for this whole types of testing design. So thank you for this.